Okay, hello everybody. Today we are going to talk to you about signatureless breach detection under the microscope. So, my name is Olli Pekka Niemi. I'm currently a Chief Research Officer of StoneSoft. And in StoneSoft I was the founder and the head of the StoneSoft Vulnerability Analysis Group. And I've been in StoneSoft since year 2000. And StoneSoft was just recently acquired by McAfee, so actually we are working for McAfee now.
And I'm Antti Levomaki. I've been since 2004 working at StoneSoft in R&D.
So we will discuss the problems that we have identified in signatureless attack detection and sandboxing as well. And we will disclose our findings. And we will go deeply through one of the market-leading products. So you will learn what are the limits of a signatureless breach detection, and there are many things that you should know. So first of all, a little background of the signatureless breach detection, and then we go straight into FireEye, which is the box that we have been using to do our analysis. So we actually have the FireEye box right here, so it's running. And we will be doing live demos. So breach detection and attack detection, it's the signatureless attack detection, it's becoming the hot topic. I mean, there are so many zero-day vulnerabilities used by real attacks. So vulnerabilities are found on the wild and not found by the security researchers. So signature-based IPS and IDS systems, they are lagging behind, so that has actually created a need for a signatureless breach detection. So one of the techniques that the signatureless breach detection devices use is called sandboxing. So we have analyzed the network-based sandboxing technique and actually found serious issues in the concept. And like I said, we did our analysis on FireEye, which is the market-leading solution right now. So this is what they say, that the FireEye is the leader in stopping advanced targeted attacks that use advanced malware. So, and these are the features that they advertise. So they say that the FireEye box is tuning-free, and then they say that it blocks zero-hour attacks and blocks APT, blocks outbound data, exfiltration callbacks, and claim that it blocks 90% of the modern malware attacks that the other systems simply can't detect. So this is a challenge that we set to ourselves. If we have this device that is designed to stop APT, it must be difficult to attack through the box. So, the FireEye attack detection methods. The analysis was done on this FireEye Web MTS 1310. So we looked inside the box, what's in there, and we found that it's actually running on it's a Linux running on an AMD Opteron processor, and there is 4 gigs of memory. So the box, it's not very powerful in terms of computation. So AMD Opteron is quite old CPU. So, and only 4 gigs of memory, that's not much. So it's running Linux, and then all the virtualized machines inside, they are run on KVM. And then they also internally run Yara, ClamAV, and Snort for a breach detection. And then there is a lot of their own stuff as well. So, how does the box work? The idea of the product is to run all content downloaded from the web. And that content will be instrumented in the virtual machines. And if there are any changes in the virtual machines, it will be detected, and basically that is how they say that they can prevent zero-day attacks. So if attack is able to compromise the client inside the virtual machine, it will or have compromised the real client as well. So once the box detects evil URLs, these will be submitted to the cloud, and other FireEye devices may then learn these bad URLs from the cloud. So the FireEye, it records network traffic, and it analyzes traffic to TCP ports 80 and 8080 for HTTP requests and responses. So, and if there is a suspicious traffic, it will replay the traffic into virtual machines inside. And for example, for a HTTP connection, the virtual machine that the connection will be replayed into is selected by the user agent that is in the HTTP request. And then the content will be run inside, so in the virtual machines in suitable program. So if the download was a PDF, then it will be fed into PDF reader. If it was HTML, it will be fed into a browser and so on. And then the box also runs static analysis with Yara and performs antivirus analysis using ClamAV for some file types. At least PDF is analyzed by ClamAV as well. So this is a picture of how it works. So first we have the client request. So this is what happens, is the real connection. So a client is downloading something from the internet, and it's lured to a malicious server. So the client requests for a file, and then the server will reply, and the reply will be malicious. So the FireEye device, it actually takes a PCAP of the session, and then it selects the virtual machine. It'll analyze the session based on the URL, based on the user agent, and then it will replay the attack. So the FireEye analysis always happens after the attack. So if the attack it was successful or it's going to be successful, it was successful. So the FireEye device is more like a intrusion detection, breach detection, but it's not prevention device. So inside the FireEye, the VX client, so the virtualized machine, and the real browser inside there will actually connect into a simulated FireEye's internal HTTP server, and that HTTP server will fed the same content as the malicious HTTP server in the internet. Will fed the same content to the browser, and then the virtualized browser will download it, and if the browser or the client got compromised, then the FireEye will actually alert that there was a compromise, and then it will actually also update the URL filter so that the URL in the internet that will be added to the URL filter list, and connections to that side will be blocked if it goes through the FireEye device. So I just have two PCAPs here. So it's the original PCAP on the left. So there you can see that there's actually user agent is a Mozilla Internet Explorer, and then the virtualized PCAP, you will see a different virtual agent. It's the same browser, but maybe a little different version. So that will show you that it's really run inside. And the FireEye device, it provides you PCAPs. So it provides you the original PCAP of the traffic that happened, and also it provides you the PCAP that it creates once it simulates traffic inside. So the FireEye device runs a maximum of 4 KVM virtual machines, and it comes with 5 pre-installed REST images. So there is a Windows XP and Windows 7, and there is no documented way to change the pre-installed images or to add new ones. So the FireEye device is completely unsupported for an Android OS X or Linux attacks. So once the FireEye device analyzes the traffic that it records for HTML, the appliance must have exact match for the browser HTTP user agent. So if the real client who is getting attacked is using a different browser than what's available in the FireEye device, then that connection won't be analyzed at all. And then the PDF files, for example, that you download, they are actually analyzed in all Quest images. So whenever the FireEye device sees a PDF file and it decides to analyze, it will start all 4 virtual machines, 4 out of 5, because it can only run 4 virtual machines at the same time. So it will start all 4 virtual machines and gives the PDF there for analysis. Then the FireEye device, there is also URL filtering, so you can deploy it as into a tab, or you can deploy it inline. And if it's an inline configuration, then there is the URL filter that can actually prevent the access to some malware sites. So, breaching the breach detection. Let's select an old Windows XP exploit from Metasploit, and that's detected by the FireEye. So the exploit is against CV 2010 0806. So our attack actually opens a command shell from the victim, and once we run the attack, it'll take 2 to 4 minutes for the FireEye box to detect that was an attack. So after 2 to 4 minutes, the box will report that there was an exploit browser in its alert log. And if the exploit is not detected, there is no notification that signals that any analysis was ever made. So it seems that it's really slow to test and find out how the box works. But luckily, you can root the box. So once you have a root access to the box, then you actually see how it works. So let's do a demo.
Okay, so here's the basic web GUI, which has logs and summaries and stuff like that. We have an This is the exploit we are going to run. It's from Metasploit, just an HTML page. We are sending via Google web server to a Windows XP client that's connected to the other side of the inline interface. So now we got a request. We got a command shell, and we don't have anything still in the logs because it's still analyzing the traffic. But with this better shell access, we can look at the warm messages where we get a scrolling log of all actions made, which would be that it started to analyze a page in a virtual machine. And we also found a debugging interface from the box that can be used to get more real-time data out. So this would mean that it's still analyzing the previous content. And this main GUI is not saying anything yet. So it's slightly easier to follow what it's doing when you're looking at the actual messages and not waiting for a log to appear.
Okay. So just a tailing bar of messages, or using the Jape debug console, we can actually see what's happening in real time, and we don't have to wait for the logs to appear on the web interface. So Our attack methodology is that we will attack on the traffic capture, and then we'll also attack on the down selection, and then we attack on the virtual machine execution. So we will first attack against the traffic capture. So if we can bypass the traffic capture, then there won't be down selection and there won't be VX execution. So that'll actually bypass the whole device. So we've been looking on different vulnerabilities in network level, and we have found several issues. First of all, IP version 4 fragmentation is not inspected at all. So if it is a fragmented traffic, it'll just go through the box. Then IP version 6 is not inspected, and if we use small TCP segments that are sent in this order, then those connections actually go through uninspected as well. And then it's also unable to do HTTP 09 or a HTTP port variation, and of course SSL TLS. So for SSL TLS, you need to have another box that actually terminates and decrypts the encryption. So we will now have demos on these as well.
Okay, so this was the amount of log we generated by running the exploit by itself without any evasions. And we also got a new incident here, which it has now been resolved to be an attack. It changed the operating system somehow. So now if we run the same page, so that we use IPv fragments that are at most 1432 sized, total size, so just slightly smaller than full-size IPv4 fragments. We are here. So now we now we have a demo effect. Yeah. So, no new logs in the war messages, no new incidents in the incident table. Now we even have the shell open. So the attack went through and it triggered no logging anywhere because the IPv fragments are not inspected. Then the same for
regarding the IP fragmentation, so the FireEye is completely not looking on IP fragmentation. So Antti was using quite a large IP fragment size, like 1400 something. So it wasn't like small fragment that is actually invalid, but it is large fragments, and that size fragments actually do happen in networks.
So our next method would be HTTP 0.9, where we just send the response file. We do it with netcat. We just cat the exploit netcat. And done. Got the shell again. No new incidents. No new log. Well, in Wireshark we can see that, we just sent the file.
So because we used HTTP 0.9, there are no HTTP server headers, and the FireEye box is probably looking for the HTTP server headers to identify HTTP, and because the headers are missing, it don't understand that it's HTTP, so it just bypass the traffic and don't look at all.
And the last trick is to run plain HTTP over port 443, which is odd but not illegal. So again, plain HTTP, just a different port, because only ports 80 and 8080 are inspected, it doesn't look at it.
Yeah, the FireEye box doesn't perform like dynamic protocol identification, but you need to configure the ports that you want it to look. There is a command on the console that you can actually give and add other ports or change the ports, but by default it only looks for 80 and 8080. So for some of these attacks there is actually mitigation. So if we would run a real HTTP proxy in front of the FireEye device, then that HTTP proxy will take care of some of the problems, like port variation, the port would be the same, and then if there is a TCP segmentation stuff, it'll take care of that, and also the IP fragmentation. So running a real proxy in front of the FireEye device, that will give you a lot of more value of the FireEye box. Basic squid is actually quite good. But then mitigating the mitigation, so if the hostile web server would use chunket encoding, then those chunks actually go through the proxy as well, and FireEye don't understand chunket encoding, so there we go again. Okay. So then, if we cannot bypass the traffic capture, or if we don't want to bypass the traffic capture, because there is reason to do that as well, there's down selection. So if you think about the resources on the FireEye box, 4 gigs of memory, and running AMD Opteron CPU, which is really old, that means that there is not a CPU power to do the analysis. So it actually cannot do the analysis on every file you download from the web. But it needs to select the files. So if we bypass the selection process, then we are bypassing the device again. So what we found is that if we play with the content type, we can actually bypass the FireEye box. So for example, if we use the content type text/rich text, the FireEye device don't look at those HTML pages at all, but the Internet Explorer has no problem of rendering those. So just playing with the content type, you can bypass the down selection, you can bypass the analysis. Or if we don't put a content type header at all, like if you would be using just plain HTTP 09, then we also bypass the down selection. So just playing with the content type header is really efficient. And then there is another content type header play as well. So if we use application PDF, but the file is actually HTML, what happens is that the FireEye box, oh, this is PDF. So I will now run all the virtual machines that I have, and I will put this file into the Adobe Acrobat, And of course, the other backup part won't get compromised because it wasn't a PDF, it was HTML. So the original client downloading the exploit, his Internet Explorer will look on the file and see that even though it says PDF, it's actually HTML. So I will render it, I will show it to you, and I will get compromised. But the FireEye box doesn't notice anything. And I think for these we also have some demos.
Yeah, so here we have the same file again. This time we use our content type of text, rich text. Here. Got the shell again. Nothing new in the logs, just some notifier logging. In the GUI we have the original baseline is the only one that has been detected, the one without evasions. So rich text is rendered as an HTML page by Internet Explorer and not looked at all by the firewalls.
So if the web server is a known bad host, so in those cases the traffic always goes to the down selection and the traffic will be analyzed. So when we've been testing the FireEye device, we need to change the IP address during this test. Okay. So content from normal hosts, so if there is a malicious web server, an IP address or a DNS name that has not been known to be malicious, for those servers, there's going to be some heuristics to know whether the traffic should be analyzed or not. So we noticed that if you have an exploit, and in the exploit if you have a word shellcode or the word Metasploit, those files will actually go to analysis. But if we use some other words for the names of the functions, they won't be analyzed anymore. So for that we also have a demo. So we actually looked into one of the binaries in the FireEye box. And in the binary, if you look at that, you can actually find the lists, the keywords that if one of the keywords is in the file, then analyze it. And if the keywords are not in the file, it's not going to be analyzed. So it's not that signatureless. There is actually a signature. So let's demo that.
So here's the original HTML. We have function heap spray, knobs, shellcode, all kinds of keywords. We used Metasploit to generate this originally. So then we changed them slightly. Shellcode, heat spray, nips. All the keywords are just slightly different. Okay. Yeah, this is still old log. We made a fingerprint for the original baseline request. Nothing related to detection. And no new incidents or log here.
Do we have the original attack already detected on it?
Yeah.
Yeah. Okay.
Yeah, it's the only one seen baseline.
So the first baseline attack, that was one without evasions. That's not being reported detected. So just using these or not using these certain keywords, you can actually bypass the analysis. So I don't know, maybe the heat spray and shell code will be bad words in the next update. I don't know. So I think that we should change the function name into Google or something like that for more fun. Okay, so we bypass the traffic capture and bypass the down selection, and now we could go against the VX execution. So the zero-day attack detection of the firebox is based on changes in the virtual machine. So how we can bypass the virtual machine execution? There are many ways, but we have looked on some really simple methods to do that. So the virtual machine is fed with payload recorded from the original execution. So the FireEye is running the same or simulating the attack again inside it. So it's actually like a traditional man-in-the-middle situation. And that has been researched a lot. For example, Diffie-Hellman. So what we do here is a really simple thing. So we have a exploit HTML page that triggers a request to the server with some random data, and we use JavaScript that sends the current timestamp. So the server will echo the timestamp back, and then the client validates that the timestamp is the same, then run the attack. If it's different, do nothing. So I have a nice picture here. So first, this is the attack happening, the real attack happening. So the victim client is doing a request to the malicious server, and then the malicious server will send back an exploit HTML, and then the victim will send its current timestamp to the server, and the server will echo it. So now the JavaScript in the client that's going to be compromised compares the timestamp, and it sees that, okay, I got the same timestamp back. So this must be a real connection, and I'm not in any virtualized execution. So it will exploit and compromise the host. Now, what happens inside the FireEye? So the virtualized client is generating a request, and it uses the original URL. And then there is the FireEye simulated HTTP server, and it will play back or send back the recorded exploit, recorded traffic from the PCAP. And now the virtualized client, which is actually a real client inside the FireEye box, will send its current timestamp to the server. But since the server is simulated, it will send the original timestamp from the PCAP. And now, once the virtualized client gets the server reply, it'll see that, oh, this timestamp is different what I got echoed back from the server. It's not the same that I sent. So it's a challenge response. So what happens is that the virtualized client won't be compromised at all. And it can calculate, for example, P. So it notices that different timestamps, I'm in virtualized execution, I don't want the exploit, I do something else. Maybe I consume all the resources of the box that tries to analyze me. So the FireEye box won't detect any attack, but there is a compromise happening. And for that, we also have a nice demo.
Okay, so here. Let's see. This is the messages log. So this time we got again, now it was selected for execution. We got a new incident. We also got a shell, so the exploit worked. What happened is we just modified the exploit so that it just sends the timestamp, compares it, and does nothing if it fails, because we didn't want to DOS our own box. So this could be made arbitrarily complex. This is just a proof of concept with timestamps that can be easily handled with automated or a man in the middle. So here's the echo with our request with our current timestamp. Here's the echo, just this time value. And now this incident was not anomalous, it did nothing, no changes to the operating system, and it was not reported as nothing evil happened.
So we have now attacked all the 3 steps. So the recording and the down selection and the virtualized execution. But if our attack was still detected, then there is a URL filter. So of course we need to bypass the URL filter as well. So all the detected malicious URLs are submitted into the cloud and thus ultimately into all the cloud-connected FireEye devices. And the FireEye's URL filter validates all URLs that go through the box against the cloud-originated database. So access to known bad URLs are blocked. The URL filter, by the way, it uses Snore to prevent access to the bad URLs. So the FireEye box is generating a dynamically blocking Snore rules. So this is just one example of the dynamically generated Snore rules. If you get a root access to the FireEye box, then you can actually see all these things happening quite easily. So if you wanted to bypass the URL filter, of course the easiest way to bypass URL filter is that every time use a different URL. If you change the URL just one character, it's going to bypass the URL filter. So if there is a malicious web server, every time it gives a malicious file, every time a different file name, you'll never get to the URL filter. Then, a better strategy is to use a redirect into exploit. So if you have an attacker-controlled web server, you can actually have a static URL, and when the client always connects to the static URL, but that URL is actually a redirector, so every connection to that static URL will be directed into another URL, which is different every time. So the FireEye box is actually looking on the last URL, so it'll never learn the static URL. So this kind of simple redirection attack is all one needs to bypass the device or the URL filter every time. And this actually is a strategy that has been used by some current malware. And then we have also bypassing URL filter by controlling the TCP client. So a TCP server, such as the web server, can actually control the segment size that's sent by the client. So the server, you can say that my TCP window size is really small, so that actually enforces the client to use small segments. And so by enforcing the client to use small segments, the FireEye box actually won't prevent, so the URL filter can be bypassed. The FireEye device actually requires that the whole URL fits into one TCP segment. So if the URL is larger than the TCP segment, then the URL filter is bypassed. So if the attacker always use like 1500 or longer URLs, those URLs will never be stopped by the FireEye's URL filter. So for these we also have demos.
Okay, so now we're trying to access the same URL that was already blocked as a bad URL. Cool. So now we get access denied, potential threat detected, and a new log that somebody is infected. So what we do is we use a web server that has a small receive window, 128 bytes, to access the same URL. And now we get no denied. Whoa. Something bad happened. Let's see. Yeah, it started analyzing because now we did no other evasions, we just bypassed the URL filter. So we got into analysis again. We have a new incident under handling. And I guess we should have a shell somewhere. Yay, it's just slow because the small segments cause the attack to go slower. So here, yeah, here's the URL. URL fits into the segment, but the host header does not fit, and there's no signature. It needs to see both URL and host header, so it doesn't match to this packet.
Yeah, actually that is correct. So it needs to, the URL and then also some other headers need to fit on the first segment, or otherwise the URL filter is bypassed. So some conclusions. So it's really not an inline device in the sense that it's more like an IDS. So all the attacks go through a device, and after the attack is successful, let it simulate it and find whether the attack was successful or not. The only way how it prevents attacks is that there is a bad URL, but even the URL filter can be bypassed. And then we actually noticed that it's not so signatureless. It's actually running ClamAV, it's running Yara, and if it is a HTML attack against the browser, it looks for keywords that are actually taken from Metasploit. So it will probably see all the attacks generated by Metasploit if you use the default shellcodes, default heap spray. But if you write your own exploits and avoid all the hacker names for functions, it won't analyze it. But maybe all the bad guys, all the APG guys, maybe they are using Metasploit as well. And then what we noticed is that if you use real HTTP proxy in front of the device, that'll actually help a little bit, but it won't fix all the problems. So thank you.
Thank you, that was really interesting. Did you say that FireEye gave you captures from within the virtual environment that it has?
You can get capture from the FireEye device.
Yeah.
So if it sees an attack, alert it. There is you can download the PCAP. You can download both. So Antti will show you.
So here from the detected incident.
Can you get that for attacks that it didn't detect, so just general course of what it was doing? Can you get captures at any point from within that environment?
Well, when we use the evasions, it never analyzed if it bypassed the whole execution step.
Yeah, we need an alert. Only alerts have.
Right. Yeah. Okay. I was just thinking you could confirm things like the behavior with the fragmented packets. You could see whether it was only sending the first one.
Yeah.
That kind of thing.
Yeah.
Cool. Thanks.
Have you told FireEye about these, and are they going to fix anything?
We have not. The reason is that what they did is really basic stuff, and there is so much marketing and everything that detects and prevents everything, so we just did a brief analysis. It didn't take much time, so no.
Any more questions? No? Okay, thank you very much.
Right, thanks.